Conditional probability. Sometimes the probability of an event must be computed using the knowledge that some other event has already happened. This type is called conditional probability because it has a condition already. So let's look at an example to understand this idea. Consider a bag of marbles that has 2 blue marbles and 3 red marbles, so total 5 marbles. Calculate the probability of a drawing a blue marble in the following situations. So yeah, we can use this image as a hint, but let's look at the first part of the problem is this right here. You draw a marble from the original bag. If you're drawing a 1 marble from the original bag, which you have 5 total right here, what is the probability that we'll select blue? It's 2 because we have 2 blues out of total 5. Now the second part right here, this one is conditional. What is the probability of selecting a blue marble after selecting 1 red marble from the bag? So this is conditional. So here, we already selected 1 red marble. Now from here, what is the probability of selecting blue? Well, we already selected 1, so we have 1 less total marbles. We have total 4. Therefore, this probability is out of 4. Now how many blues we have left here? 2. Now let's look at the third part. This is a separate problem. What is the probability of selecting a blue marble after drawing a 1 blue marble from the bag? So I already selected 1 blue marble here. And from here, I have 1 less because I already selected 1. What is the probability of selecting another blue marble? Well, we have total of 4. But then now we only 1 blue left because we already selected 1. So this is a basic example of conditional probability. There's a condition, something given something happened, find the probability of certain event. So here's a formula. And let me go over the formula, but many of the problems we do is we can actually think about it and make sense within the problem without relying on formula. And of course, if that making sense method doesn't work, then we can use a formula. Okay, and again, I'll demonstrate that as we do more examples later. So probability of event B computed on the assumption that event A has happened is called conditional probability of B given A. And this is the notation we use. Of course, this capital P means probability that B occurs. This vertical line means given A happened. Probability that B occurs given A occurred. Already occurred. So the probability is probability of A and B divided by probability of A. Think as the given condition probability is what we divide by on the denominator. And numerator is probably A and B. And another thing about conditional probability is oftentimes it decreases the whole sample size. Okay? So let's look at examples to understand this idea of conditional probability. So from a sample space of 1 to 10, so we have 10 numbers, total 10 numbers. Single number is to be selected at random. Calculate the probability of the given events. So let's say event A is selected numbering odd, B is selecting multiple of 3. So what's the probability of selecting A? Well, A, we can list all the events, all the sample space. Our numbers are 1, 3, 5, 7, and 9. And multiple of 3 is 3, 6, and 9. So what's the probability of A? Well, there are 5 items, 5 numbers out of 10. What's the probability of B? Well, there's 3 numbers out of total 10 numbers. So these are just basic probability we saw earlier in earlier video. Now let's find probability of A and B. What's the probability of A and B? What do they have in common? Right? Well, 3 and 9, 3 and 9. So A and B has two numbers together. So there's 2 out of 10. Now, let's look at conditional probability. This one's asking, find the probability of B given A. So let me write that until we get used to it. Probability of B, this vertical line means given A. So given we already selected multiple of 3. No, excuse me, given A. A is the odd. So given we already selected odd number, what is the probability that is that odd number is multiple of 3? That's what we're finding. So let me note here, given A means we selected one of 1, 3, 5, 7, or 9. So now instead of looking entire sample space of 10 numbers here, it decreased the sample space to 5 numbers because it's conditional. We're only looking at these odd numbers. Given we selected odd number, what is the probability that out of these 5 numbers, we get multiple of 3? Well, that's 3 and 9. So that's 2 out of 5. So answer is 2 out of 5. That's the probability. And of course, this we try to make sense out of this in given context of problem. We could also have used a formula. The formula of this is probability of A and B divided by probability of A. Well, probability of A and B, B and A, they're the same thing. The order of N doesn't matter in terms of probability. What matters is we're dividing by the probability of the given condition. Well, we know that probability A and B was 2 over 5, or excuse me, 2 over 10 right here. Divided by probability of A is 5 over 10. And if I do this calculation, let me do on the side right here. Well, dividing by fraction is the same thing as multiplying reciprocal. So I multiply reciprocal of this. 10s cancel out. I get 2 over 5. So we could also have done with the formula. Either way is fine. Let's look at this example. Given a family of 2 children, so that's the condition, find the probability of each event. So here, the sample space is again defined by the condition, the conditional event. So here, the 2 children means you could have boy, 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 girl, girl, boy, or girl and girl. So 4 cases. So out of these 4, what's the probability that both are girls given that at least one of them is a girl? So from these 4, we look at least one of them is a girl. There are 1, 2, 3. At least one of them is a girl. So our sample space for this problem is 3. Boy, boy, girl, because at least one is girl. I'm trying to list this condition. Boy, girl, girl, boy, girl, girl. So out of these 3, what's the probability that both are girls? Well, 1 out of 3, right? Both are girls given that older child is a girl. Okay. So let's say this is order. First is older, second is younger. Well, in that case, older child is a girl will be this one and this one. So this is first child, second child. This first child, second child. So we have two cases in this case. What's the probability that both are girls on these 2 cases? Well, only one of them, so 1 out of 2. So we can limit the sample space, or we can just list all the sample space to find the conditional probability in these kind of problems. Independent events. So 2 events, A and B, are independent events if the knowledge about the occurrence of one of them has no effect on the probability of the other one occurring. So that's the meaning of independence in terms of probability. In terms of formula, that means that probability of B given A is same as probability of B because the condition of A does not affect the probability of B. Or we can also say probability of A given B equals to probability of A. Same meaning here. This means that condition of B does not affect the probability of A. So whatever the probability of B is, it does not affect the probability of event A. That's why it's just probability of A. So when to use this formula? There are 2 cases. we can use this formula to verify that if event A and B are independent. Because sometimes given in context, it's not so clear if events are independent or not. Some things we can use out of common sense. But even then, sometimes people can argue differently. But I mean, we could argue that, for example, rolling a die and getting a 6 and drawing a heart from a deck of cards, those two events are independent. That does not affect its probability, right? But mathematically, if we want to be clear and 100% sure that they're independent, we can use this formula to compare the numbers to verify if A and B are independent or not. Second case is if you're told A and B are independent, so it's given that how the A and B are independent, then there's fast way to calculate probability of A given B, which is just probability of A. We don't need to use the formula we saw earlier for the conditional probability. Because if independent, we can just find the probability of A. So let's look at some examples. A single card is drawn from standard 52 card deck. Find each of the following given events. Again, event A is selecting a face card. There are total 12 face cards. 12 face cards, Jack, Queen, and King for each suits. And selected card is black. There are 26 black cards, clubs and spades. So what's the probability of selecting a face card? Well, there are total 12 face cards out of 52. This is just regular probability, elementary, probability, basic probability. No condition, just doing, how many black are there? 26 out of 52, which is 0.5. So here, this is finding probability of B given A. Remember, this means given. So that means A, given A. Given the card is face card, what is a probability then? Is that their face card is, what is the probability that face card is black? So let me write that. So this is finding probability that single card drawn is black given it's a face card. Right? Well, given face card, that means we're only looking at face cards. So we know there's only total 12. Well, out of total 12 face cards, let me write, there are 3 diamonds, 3 hearts, 3 spades, and 3 clubs that are face cards. FC means face cards. So that means there's total 6, because spades and clubs are black. There are total 6 out of 12. So probability is 0.5. So again, what's happening when we're doing conditional probability, the sample space total that we're divided by this number decreases. We're not looking at total 52 cards. We're looking at only face cards, given face cards. So use the above result to determine whether event A and B are independent. So again, the best way to do it is just comparing these two values, probability of B given A and probability of B. If they're same, they're independent. If they're not same, they're not independent. Well, we just found this probability of B given A was 0.5. And so was the probability of B earlier we found, 0.5. And oftentimes, these are not as intuitive in our minds. That's why we have to rely on formula to compare the values. So since they're equal, let me write this, since they're equal, A and B are independent. That means event A and B do not affect each other's probability. So let's look at probability of events involving and. We saw or before, now we're looking at and. So and is multiplication. We're using multiplication rule of probability. And or was addition. So for multiplication, if A and B are any two events, then probability of A and B equals probability of A multiplied by probability of B given A. The conditional probability we learned. If A and B are independent, of course, if A and B are independent, then probability of B given A is same as probability of B. So we just multiply two probabilities together. Okay, so the formula is different depending on if events are independent or not. So let's look at an example here. Each year, Carrie adds to her book collection a number of new books. She has categorized each of 20 new books as hardcover, paperback, fiction, or nonfiction. The information is displayed in the table below. So here, what is the probability that if she randomly chooses one of the 20 books, that it will be hardcover? Well, if you look at hardcover, there's total 8 out of total 20 books. So this probability is 8 out of 20, which is same as 2 over 5 or 0.4. What is the probability the book is fiction given it is a hardcover? So here we can just look at the section where it's hardcover. Well, hardcover, there's total of 8 books. So out of these right here, what is the probability? We're only looking at here because given hardcover, what is the probability that is a fiction? Well, out of total 8 books, there are 3 fiction. So the hardcover, there are total 8. Well, how many are fiction? 3. So that's the probability for this problem. Now let's look at N. What is the probability of selecting a hardcover and it's a fiction? In this type of problem, if you can make sense, we don't necessarily need to use the formula. Here, well, we just read the table. Hardcover is this row right here. And fiction is right here. Right? So what's hardcover and fiction? Well, there's 3 hardcover and fiction out of total 20 books. So answer is just 3 out of 20. But let's also try this problem using the formula. We should get the same result. Let's call it this is event A. Fiction is event A. And you know what, let's use this one. Hardcover, let's say, is event A and fiction is event B. So we want to find probability of event A and event B, which is probability of event A multiplied by probability of B given A. So probability of hardcover, we found it here, 0.4. Probability, well, let's actually keep it fraction so we can multiply easy with the fraction. 88 over 20 we found earlier here. And probability of B given A. So probability of fiction given is hardcover, which you also found here, 3 over 8. And if we multiply these two numbers, we get 3 over 20, which we got here. Okay, so it's not written here, but why don't I have you try one more? Why don't you pause the video and find the probability that it's a paperback. Find the probability using this table. Paperback, given it's a fiction. Given it is a fiction. Okay, so pause the video. And when you're done, I'll go over this. Okay, so let me go over this. Paperback. First is given it's a fiction. So that means we're only looking in only fiction books. Fictions. So sample space, instead of 20, we're looking only 11 total books. So given fiction, what's the probability as a paperback? Well, there's total 8 that are fiction. So 8 out of 11. So here are some tips on how to distinguish mutually exclusive from independent. We should not confuse those two things. Mutually exclusive comes from usually when we do the problem with probability of or A or B. Are they mutually exclusive? Independent comes from when we are doing probability of A and B. So although mutually exclusive probability and independent probability are quite different, in practice it can be difficult to distinguish them. The following diagram can help us understand if they're mutually exclusive, independent, or neither. So does the occurrence of one event prevent the other event from occurring? If yes, then they're mutually exclusive. If no, then we have to answer another question. Does the occurrence of event change the probability of other event? No, then they're independent. Yes, they're neither mutually exclusive nor independent. So something to keep in mind. Oops. The important thing is that they're not the same thing. The mutual exclusiveness and independent, they're different ideas. Now, determining which method use. We have studied several methods finding probability of A and B, A or B, or at least one, or also conditional probability. So following some of these can help us calculate. Okay. So, does the event involve and or at least? If it's and, we have to figure out if they're independent. If they're independent, yes, then we multiply these two probability to find the calculation of the probability A and B. If they're not independent, we need to find this conditional probability B given A and multiply the probability of A to find probability of A and B. The idea of at least was similar to complement. Right? 1 minus none. At least 1 is 1 minus none. For or, which was addition, if they're mutually exclusive, we just add two probabilities. If they're not, we need to subtract where they overlap. But you can also think, the way I like to think about this, for this formula especially, well, if they're mutually exclusive, essentially this probability is 0. So we're subtracting 0. And even also for the independent, non-independent. Well, if these two events are not, if they're independent, this probability is just probability of B. That's what we get here. Okay, so something to keep in mind. But the important thing, really the main point of me going over this page is that we need to distinguish between and or. And let me write the symbols one more time. And symbol, we use this symbol. And it's not alphabet, it's its own symbol. And for or, we use this union symbol. This is not letter U, this is its own symbol, U. That shapes like U, but it means union. But it's easier to remember because it looks like U, so we can think of this as union, and this looks like alphabet N, which the N is in A and D, right? So keep that in mind. So the important thing is we need to differentiate between probability of and probability of or. So A and B, A or B.